Greetings, everyone. Welcome to our presentation on virtualized congestion control. This presentation is part of our coursework for CS 643 Cloud Computing under the guidance of Professor Kazi. The paper we focused on addresses a real and growing challenge in modern data centers. How to ensure fairness when legacy applications compete with modern ones for bandwidth in sharing environments. We are Group 3, and our team consists of myself, Jyotsna, Vishal, and Pranav. In this presentation, we will take you through the key problem, how existing solutions fall short, the solution proposed in the paper, and its evaluation. Let's get started. I'll begin with the introduction, the problem statement, and background on the data centers and congestion control. Then I will explain the unfairness problem, why existing solutions fall short, and introduce the paper's proposed solution. After that, Vishal will explain the technical design, architecture, and the hypervisor translation techniques used in this VCC. And finally, Pranav will cover the simulation setup, key environmental results, experimental results, and we will conclude with our main learnings from the paper. Legacy applications using older TCP protocols can't fairly compete with modern apps using ECN or DCTCP in shared data center networks. This unfairness causes them to be starved on bandwidth, risking SLAs violations and poor tenant performance. The paper focuses on solving this fairness problem without requiring app upgrades and hardware changes using a software-based solution called virtualized congestion control. Ensuring fairness isn't just a technical challenge, it's a crucial for business reliability and tenant satisfaction. Understanding data centers and congestion control. First, data center is a huge building filled with servers that run applications and store data. Big cloud services like Amazon Web Services and Microsoft Azure are examples of global data centers. Now, these data centers don't just serve one company, they usually run in a multi tenant environment. This means that many different customers' applications share the same physical infrastructure, the same servers, and the same network bandwidth. Imagine it like a busy highway where every customer's app is like a different car on the road. Naturally, managing this traffic becomes super important to prevent congestion. That brings us to the congestion control. This is the system in networking that makes sure data flows smoothly. If too much data tries to move at once, congestion control slows down some apps to prevent overload and keep everything fair and stable. Modern data centers use advanced congestion control methods like ECN, DCTCP. These protocols help maintain low latency and fair bandwidth sharing. But here is where the problem starts. Not all the apps are modern. Many apps are legacy applications built years ago, running on older TCP versions that don't support ECN or DCTCP. So, what's happened here? It's like putting an old car on a fast moving freeway. These legacy applications struggle to keep up getting less bandwidth even though they are supposed to share fairly. This kind of unfairness can even violate service level agreements, which guarantee performance to customers. The paper we are presenting today focuses exactly on this issue, how to handle fairness in this busy shared environments when legacy applications and modern applications compete. Now that we understand the basic, let's move on to the real world problem and its evidence. This graph here shows how legacy applications suffer in multi-tenant data centers, potentially violating SLAs. The paper's solution, Virtual's ECN, aims to eliminate this unfairness by enabling legacy flows to compete fairly with modern flows. If you can see the graph, the ECN flows dominate, while the non-ECN flow is starved, achieving just 10% of their good put. Why does this happen? It's because ECN detects congestion early and adjusts smoothly. But non-ECN flows keeps sending until packets are dropped, triggering timeouts and aggressive backoffs. Virtual ECN mimics Virtual ECN mimics the ECN behavior, restoring fairness with near in identical throughput. But there is a catch here. The experiment uses a controlled setup. Would we see the same starvation in a large data center with thousands of flows or different queue policies? The paper does not say, which makes us wonder about its real world applicability. Still, this data sets the stage for why we need a solution like virtualized congestion control. But first, let's explore what's been tried before and why those approaches fall short. So, what's been tried to fix this unfairness in data centers? First, let's see the rate limiters. These cap bandwidth for each app to enforce fairness, but they are like putting a speed limit on every car. That means they can waste up to 50% of bandwidth when demand shifts. Second is the switch modifications. These tweak network hardware to prioritize legacy applications, but they are expensive and complex, especially for data centers with thousands of tenants. And the third is the TCP proxies. They act as the middlemen to translate legacy traffic, but they mess with TCP's reliability and risking app errors. Each approach has its flaws, so the paper proposes virtualized congestion control, which uses the hypervisor to dynamically manage the traffic. So the solution is virtualized congestion control. So the solution proposed by the paper, it's like the VCN is a software layer inside the hypervisor. So more precisely, a type 1 hypervisor, which directly manages virtual machines on the physical server. Its main role is to act like a translator between old and new congestion control. The legacy app continues using its old congestion control protocols, but VCC repackages that traffic into modern ECN or DCTCP behavior before it hits the network without needing any changes to the app or guest OS. So here in the diagram, as you can see, the legacy app sends its normal traffic. The VCC layer interrupts and tweaks it, then forwards it as modern ECN and capable traffic to the data center network. This way, legacy applications can compete fairly even in modern environments. It's a smart software only solution, but it's not perfect. It works only for TCP flows and requires that the hypervisor is in control. Also, the paper does not address non-TCP traffics like UDP. Now that we have seen what VCC is and how it works, let's dive into how it solves the problem we saw earlier compared to the older solutions. Now that we understood how VCC works, so let's move on to the problems and so first, rate limiters, and what VCC does is it provides dynamic bandwidth allocation and adjusting in real time, so bandwidth is fully utilized. Second is the switch modifications. So this is expensive and complex to manage at scale previously, but when VCC comes into picture, it's completely avoids this issue because it's a fully software-based solution. No hardware changes are needed. And finally, TCP proxies. These are like um, um, let's say VCC keeps the full integrity of TCP intact, and ensuring applications stay reliable. So, what's clear in that VCC is not just a clever idea, it overcomes the key faults of traditional approaches in a simple and scalable way. Uh, um, let's see this critical reflection over here. That means it could smartly switch with AQM, which is active queue management, which controls congestion at the switch and fix this unfairness without VCC. The paper skips this idea because it only focuses on a software solution instead of hardware changes, which leaves us wondering about other possibilities. So, next we will dive into VCC, how it works, and make it smart and better. With that, I will hand it over to Vishal, who will take you deeper into the technical design of it.
Yeah, thanks, Josna, for briefing about the topic. So let's touch upon again, like a bit more about VCC, what's the architecture, and then we can go into the translation technique. So, as we have seen how legacy VMs get starved by the modern TCP, right? And updating them is tough. VCP fixes this by translating TCP in the hypervisor. Let's see how that works. So the VCC architecture is all about the hypervisor sitting between the VM and the network, as shown in this figure, tweaking the TCP packets to make a legacy VM act modern. How VCC sets ECN flag in packets to avoid congestion while hiding those changes from the VM. It's like a translator rewriting messages on the fly. The hypervisor intercepts packets, modifies them, keep the TCP working smoothly. There are different ways to do this, and we'll explore those techniques next. So there are main three types of translation techniques. First one being intrusive, then moderate techniques, and then the lightweight techniques. So moderate techniques acts like a middleware, splitting the connection or buffering packets, but they are chunky. Whereas lightweight techniques are the simplest. They tweak packet headers directly, like what we have saw in the earlier figure with the ECN, and we'll break each of this translation technique one by one. So let's start with the intrusive technique, which is write guest memory. Here the hypervisor goes into the VM's memory and rewrites its TCP code, like swapping out old TCP from the DC TCP. It's super powerful because you can change anything, but it's really tough to get right, and tenants don't trust the hypervisor messing with their VM's private memory. It is also slows things down. So the paper skip this. It's too risky. Let's move forward with the next technique, which is read from the guest memory. This is also a highly intrusive method. Here VCC reads it reads it to track. Here instead of changing the VM's memory, VCC actually reads it to track the TCP setting like the congestion window. This helps VCC translate without rewriting the code. Is less evasive than writing, but still breaks the privacy. Tenants don't like it, and it's also slows because reading memory takes time. The paper doesn't use this either. It's still too messy. Now let's move to the moderate techniques. So first, moderate. Now to start with the moderate technique, starting with the split connection. Here VCC acts like a middleman, breaking the TCP connection into two parts. The hypervisor talks to the VM one way and the network another, controlling the flow. It's great for tweaking things like multipart TCP, but splitting the connection breaks TCP normal rules, which can mess up the apps. It's also tricky to set up. The paper skip this for a simpler solutions, which we'll discuss, but it's useful in some cases. So let's have a look at the another translation technique, which is buffer packet ACK, where VCC holds onto the packet or ACKs to control what they are sent, smoothing out the traffic. This helps with the problem like TCP incast, where too many packets jams the network. But buffering needs a lot of memory and adds delays, which isn't great for the speed. It's also tough to manage with the big packet, and the paper doesn't use this either as it slows down the process in most of the cases. So we'll just jump on to the last moderate technique, which is duplicate ACK. Here, VCC sends extra ACKs to the VM, tricking it into thinking the packets were lost. This also makes a VM slow down, like hitting the brakes on a moving car, but it's quick way to control speed without buffering. But it can confuse the VM by breaking the TCP rule, and it only slows things down instead of speeding them up. The paper doesn't use this as well. It just discuss. It's too limited. So we'll just move on to the lightweight techniques. So lightweight techniques. First we'll discuss the handshake technique, where VCP tweaks the TCP handshake to add a feature like ECN, making the network think the VM supports it. For example, it sets ECN flag in SYN packet, but hides them from the VM. It's super simple and doesn't change the VM's code. This sets up better congestion control without any hassle. The paper uses this in experiments to boost the fairness. So we'll move on to the next technique, which is throttle the receive window, where VCC shrinks the receive window in ACKs to limit how many packets the VM sends. For example, if the if network is congested and VCC lowers the window to slow the VM, mimicking ECN, it's easy. It just uses 37 bytes per flow and keeps the TCP happy. The paper's experiments shows this makes legacy VMs as fair as modern ones. It's a big reason VCC works so well in the data centers. Uh, so so after discussing all these techniques, so what's the big picture? So VCC techniques lets the data center run modern TCP without touching legacy VMs. Intrusive techniques are too evasive, tenants won't trust them, and whereas the more moderate techniques like splitting connections or buffering causes delay and breaks the TCP rule. So lightweight techniques like tweaking the handshake or windows are simple and reliable, and the experiment which we'll talk about later in the presentation as well proves they deliver fairness and better bandwidth. This idea of virtualizing algorithm is a huge win for a cloud provider like AWS. uh, okay, so I'll just hand it over to Pranav for demonstrating the solution.
Yeah, thank you, Vishal, for that. Now, coming to the demonstrating the solution, let's now shift focus to how the authors validated their solution, that is the virtualized congestion control. They did this on two key fronts, that is, first theoretically and then the prototype implementation. Coming to the theoretical part, they defined a transformation function, that is the T of X, that intercepts legacy TCP flows and reshapes them to act like modern ECN flows. Formally, it satisfies the main function, that is the g of T of X is equal to f of X, where g function is the legacy TCP logic and f of x represents the f of n represents the behavior of a modern ECN aware flow. This elegant formulation means legacy apps can behave as if they were ECN capable without knowing it. Second, coming through the prototype implementation, they built this translation layer within the Linux kernel using the Mininet, and then inside the VMware's ESXi hypervisor using the virtual switch. As you can see in the slides, both the diagrams and the functions. In both the cases, they achieved ECN-like behavior for legacy flows using receive window throttling again, all in software and with no changes to apps or hardware. So coming to the next slide on robust demonstration across systems and scenarios. To make sure the author's approach wasn't confined to a single step, they tested it across multiple environments. First on the Mininet Linux for simulation scalable testing, then the VMware ESXi for real hypervisor based experimentation, as you can see in the slides. They ran VCC, they ran the virtual congestion control under multiple network speeds, that is the 10 Mbps, 100 Mbps, and 1 Gbps links, and mixed flow types, that is the ECN, non ECN, and the virtualized ECN. This breadth of testing shows that VCC is platform agnostic and cloud ready. They didn't stop at functionality. The authors ensured repeatability and statistical significance through 140 plus test runs. Each run was time filtered, startup and teardown phases excluded for clean reliable measurements. Metrics evaluated included the goodput, fairness index, and retransmissions. Goodput is where how much useful data is transmitted, and fairness index gives us measuring the equitable bandwidth use, and retransmission is a sign of congestion and instability. Across platforms, configuration and test cases, VCC consistently improved fairness and performance, as you can see in the graphs that is there in the slides. You can see that ECN and virtual ECN show the similar behavior, whereas the non-ECN has the lesser impact on the good put. Even with the virtual ECN and non-ECN with the fairness index, the virtual ECN is 52% and non-ECN is 48%. And coming to the retransmissions, the prefer and unpreferred without VCC and with VCC, you can see a big difference. Coming to the next slide, did it work? Yes, and yes, how? So did virtual congestion control achieve its original goal? Yes. Yes, and here's why. The main research objective was to bridge legacy, TCP, and modern congestion control without modifying endpoints or hardware. So VCC succeeded by introducing a novel transition layer in the hypervisor, mathematically proving that this layer replicates ECN behavior. Building real prototypes in both kernel and hypervisor layer is also a key contribution recap. Testing across diverse configurations and workloads is also done by the VCC. In short, VCC made legacy TCP look and act modern, transparently, and effectively. Coming to the next slide on the clarity, logic, and design of the paper, which was done right according to my experience. This paper stands out for more than just technical innovation. You can also see the structure of the paper, it's very clear. The author very well shown the problem, design, prototype, results, and the insights in a very smooth manner. Diagrams like g of t of x is equal to f of x, as we discussed in the theoretical implementation, help signify complex systems. Writing style is technical yet concise and readable for all the audience out there. Each experiment aligns with a well-defined hypothesis and results are clearly presented in the paper. For the readers and practitioners alike, this makes a paper accessible, credible, and reproducible, even for those new to congestion control. Yeah. So you can see that the paper is very good in logical cohesion as well as in technical clarity and the experimental rigor. So coming to the conclusion of how the paper is written, the paper is well structured and readable and reproducibility even for those new to the computer science field. So coming to the next slide on core metrics and results, I would first like to discuss on the first metric, that is the good put. Good put basically defines the rate of useful data transfer. So you can see in the graphs which is put up in the slides that the non-ECN flows is 14.2 Mbps, whereas the ECN flows is 100 Mbps. And the author experimented using the VCC and he got a flow of 103.8 Mbps, which I would say is very good compared to the non-ECN and the ECN. So concluding about the good put, VCC fully restores the throughput to ECN levels even for legacy flows. So I would like to talk about the second metric, that is the Jane's Fairness Index. This basically measures how evenly bandwidth is distributed. The non-ECN gives us a value of 0.921 and the virtual ECN gives us the value of 0.994. So we can conclude that VCC enables near perfect fairness between ECN and legacy flows, which is a good one. So coming to the conclusion of this slide, the VCC not only catches up with ECN, it matches or even slightly exceeds it in the context of fairness and performance. So coming to the next slide on the core metrics and results, I would like to talk about the stability and adaptation. Vishal, can you go to the previous slide?
Okay.
Yeah, coming to the third matrix, that is the retransmission delay, I would like to define it as the time until packets are resent after loss or congestion. So coming to the overall explanation of the retransmission delay. Coming to the graph, I would like to say that the legacy TCP flows have suffered delay due to timeouts and congestion. VCC reduced those delays by reacting earlier, like ECN improving network smoothness. So I would also like to say that the dynamic bandwidth allocation on VMware and VCC and used port tagging to identify preferred versus non-preferred flows. It then dynamically shifted bandwidth towards preferred flows in real time. This shows that the VCC isn't just fair, it's flexible and adaptive to changing workloads and priorities. So coming to the so come here to the result of the matrix tree, I would like to say that the non-ECN flows experience sharp spikes due to the queue overflows. Here we can see in the graphs of the A graph, that is the 10 non-ECN flows, you can see the sharp spikes due to the overflows of the queues. And in the 10 ECN flows, it's just a straight line, and also in the virtual ECN flows, it's a straight line. So we can say that the virtual ECN comes close to the ECN flows in terms of retransmission delay. So we don't have the point to talk about the non-ECN. So coming to the conclusion, I would like to say VCC smooths congestion events, improving network stability. Coming to the metrics 4 of the core metrics and results, I would like to talk about the dynamic bandwidth allocation. The basic definition of dynamic bandwidth allocation is reassignment of bandwidth between preferred and unpreferred flows. You can see in the graph there is a unpreferred flow from 3 to 1, and then the preferred flow picks up from 1 to 3, that the dark, and I would like to differentiate between the light and dark shades in the graph. So on VMware, VCC used port tagging to identify between the preferred versus unpreferred flows, and then it dynamically shifted to bandwidth towards preferred flows in real time. This shows us that the VCC isn't just fair, it's flexible and adaptive to changing workloads and priorities. So here you can see that the bandwidth shifts from unpreferred 2.5 Mbps to preferred 2.5 Mbps using the VCC in VMware ESXi. So concluding this matrix, VCC dynamically reallocates bandwidth based on flow priority in real time, which is a very good result from this paper. So coming to the next slide, and what did we learn from this paper especially? I would like to talk about the four key takeaways. The first one is the legacy TCP can be modernized. That means VCC enables non-ECN flows to emulate ECN behavior transparently via a hypervised layer translation, which already Vishal talked in the working of the VCC. So what I would like to say with this point is, with VCC, old flows emulate ECN behavior without app or operating system changes. So coming to the fairness and performance, I would like to say that the performance and fairness are restored. Legacy flows achieve good put equal to ECN flows, that is 103.8 Mbps, which we have seen in the results. We saw that the ECN gives 100 Mbps flow and virtual congestion control gives 103.8 Mbps, where you can see that it's more than 3.8 Mbps as well. So we can say that it can achieve a good put equal to the approximately equal to the ECN flows, whereas the non-ECN flows just gives around 14 Mbps of the flow. So it's a very big difference between the non-ECN and the VCC flows. So I would like to say that the VCC gives a good put equal to the ECN flows. And also coming to the fairness index increases from 0.921 to 0.994 with the VCC. This also we saw in the results using the Jane's fairness index, where the fairness index of the non-ECN is 0.921 and the fairness index of VCC is 0.994. So it's thoroughly justified and proved in the paper as well that the fairness index increases for the non-ECN to VCC. So coming to the next key takeaway, that is VCC is practical and deployable. This can be taken from the paper where the author said that the VCC can be successfully implemented in both Linux systems and the VMware. In Linux system, he especially mentioned the Mininet, and VMware, he especially mentioned the ESXi. So it's tested in both the Linux and VMware environments. So it works on varied link speeds and RED configurations as well. So this is one of the key takeaways from the paper. Coming to the last key takeaway, that is the congestion control can be virtualized. This paper introduces a novel concept of algorithmic virtualization of congestion control, decoupling the network control logic from endpoints. So I would like to say that it lets us change the algorithm beneath without changing the logic above. So the internal working of this algorithm does not change, but it lets us change the internal working of the algorithm without changing the outside what the audience can see. I can also say that this could redefine how we design the software defined networks. So I would like to say that VCC is very useful in the computer cloud environment field, and also it's very deployable and practical, so it's good to do it. So coming to the conclusion side, and I would like to say thank you for your attention. And I would also conclude this presentation by saying that virtualized congestion control is an elegant deployable solution that brings fairness to data centers without rewriting history or legacy code. And also, I would like to say that the non-ECN disadvantages can be overcome through the VCC, and also it can regain the legacy of the ECN networks. So that's it. Thank you from our team.
Yeah, thank you.